Welcome back, focused learner, to today's explainer. We're taking what might honestly seem like the dry, everyday mechanics of measurement, and we're going to transform it into a highly tuned detective toolkit for physics. We're zeroing in on the P1.1 requirement in the Cambridge IGCSE Coordinated Sciences syllabus. So, it's not just about what tools to use, it's about exactly how to use them to uncover the hidden rules of the physical world.
Okay, let's dive right into this and ground these concepts in the real world. Think about a simple measuring jug, like one you'd use to measure milk for a food tech project. It might seem mundane, right? But measurement is literally everywhere. Before we can even think about calculating the kinetic energy of a speeding car, or, say, the resistance in some complex electrical circuit, we first have to master the absolute basics of quantifying our environment. Measurement is that crucial first step. It's the bridge between the messy physical world and the clean mathematical equations we use to describe it.
Here's our game plan for today. First, we'll look at the foundation of physics. Second, measuring length and volume. Third, tracking time accurately. Fourth, the power of averages. And finally, spotting measurement inaccuracies. Let's get to it.
Section 1. The foundation of physics and why we actually measure things.
Now, it's absolutely crucial to recognize right from the get-go that physics isn't just about passively reading facts from a textbook. You can't just memorize a bunch of equations and call it a day. It is a totally active, hands-on investigation. There's a great quote from the introduction to the Cambridge Physics Workbook that hits the nail on the head. It says, just learning your work and remembering it is not enough. You also need to demonstrate your experimental skills. This is what's formally known as Assessment Objective 3 or AO3. Basically, hands-on investigation is the true foundation of science. You have to be able to safely handle apparatus and generate reliable data. Because, think about it, if your initial measurements are flawed, literally every calculation that follows is going to be wrong.
Moving on to Section 2, measuring length and volume, or the space things occupy. So, our first major practical challenge is quantifying physical space. And this actually brilliantly illustrates how cross-disciplinary measurement really is. Imagine you're recreating Project P1.1 in food technology. You need the volume of milk, so you grab a measuring jug and you record your findings in liters or milliliters, right? Simple. Different subjects rely on specific instruments, but when we step into the physics lab and follow the specific guidance for P1.1 in the scheme of work, the demand for pure precision really ramps up.
Under the P1.1.1 syllabus requirement, we're directed to focus specifically on rulers and measuring cylinders. A ruler is obviously your go-to for finding a precise length. Meanwhile, a measuring cylinder is absolutely essential for finding the accurate volume of a liquid or even a weirdly irregular solid if you use the water displacement method. Choosing the exact right tool with the correct scale and resolution, well, that's step one in solving literally any measurement puzzle in the lab.
All right, Section 3. Tracking time accurately, capturing those fleeting moments.
Now we're shifting gears from stationary objects to dynamic, fast-moving events. That means breaking out the clocks and digital timers. But I have a really critical question for you to ponder here. How do you accurately measure a time interval that is actually shorter than your own reaction time? Seriously, think about that for a second. If an event starts and stops faster than your brain can even tell your thumb to click the stopwatch, how on earth can you get accurate data?
Well, the harsh reality is that human reaction time makes timing a single, rapid event, like just one swing of a fast pendulum, nearly impossible. Your standard digital timer might measure all the way down to the hundredth of a second. But if your physical delay in starting and stopping the timer adds a quarter of a second of error, well, all that incredible digital precision is completely wasted. It's just a fundamental biological limitation that we have to find a way around.
Which brings us to Section 4, the power of averages, multiplying to divide.
So, we need a mathematical solution to this biological problem. And luckily, the P1.1.3 syllabus requirement gives us exactly that. Here's how you bypass that human error. Step 1. Instead of trying to frantically measure just one rapid event, you measure the time for multiple oscillations. Say, let a pendulum swing 10 or maybe 20 times and time that entire continuous sequence. Step 2. Take that total time on your stopwatch and just divide it by the number of swings. This super simple technique gives you the average period of a single swing, totally bypassing the clumsy timing of one isolated event.
The crucial point I want you to take away here is the huge difference in reliability between these two methods. A single measurement, it's highly vulnerable to your reaction time. All your error is basically packed into one tiny time slot. But averaging multiples, that spreads that exact same reaction time error across many intervals. The error gets watered down into a tiny fraction of what it was, giving you a highly precise average for those super short intervals of time. It is a brilliant, essential trick of the trade.
Finally, Section 5, spotting measurement inaccuracies. Basically, thinking like a scientist.
You know, being a good physicist isn't just about blindly trusting the numbers you write down. It's about actively questioning them. Tying this all together, the 1.1 EG Physics Workbook gives us a great prompt. Suggest 2 reasons why the student's measurement is inaccurate. Based on what we've just covered, we can easily spot 2 major culprits. First, as we just talked about, human reaction time when hitting that stopwatch. Second is something called parallax error when reading a measuring cylinder. If your eye isn't perfectly dead level with the bottom of the meniscus, that little curve of the liquid, you are going to read the scale wrong. Actually, knowing how to use measuring tools correctly intrinsically means knowing exactly why measurements go wrong. As we wrap up today's explainer, I want to leave you with a thought for your next lab session. In your next experiment, what invisible errors might be hiding in your measurements? Are you maybe viewing your cylinder from a weird angle? Are you trying to manually time an impossibly fast event? Remember, you've now got the P1.1 toolkit, so use it, not just to take measurements, but to guarantee their absolute precision. Keep questioning, keep investigating, and as always, keep learning. See you next time.